Good morning. Morning. Assalamualaikum. Morning. Did you bring out the table? The more dynamic table. No one printed out. Okay, make sure you bring it into the in class. Next class, huh? It's easier for you to see. Now today I will proceed with chapter 3. First law analysis of combustion system. Okay, basically this chapter will use the thermodynamic concept. Okay, the enthalpy calculation, everything. Can we start? Xavier, can we start? Okay, now chapter 3, first law analysis of combustion system, where at the end of the this course you should be able to determine the heating value of fuel based on heat of formation method. Okay, solve the energy balance analysis to determine the rate of heat transfer from combustion system. So basically you will be introduced in the application of the thermodynamic tables. Okay, from first law equation, in a controlled volume combustion, we ignore the kinetic and the potential energy. Okay, and assuming no work is done. So this is an example of combustion combustion process where you have reactants, which is your fuel and your air. Okay, the reactants. So product would be your combustion product. It can be CO2, CO if your combustion is incomplete, then H2O, O2, and N2. Okay, this one is based on your fuel. Okay, based on your fuel. This is the common products. Now, the combustion heat equivalent to total heat produced by the product minus heat produced by the reactant, supplied by the reactant. So product minus reactant. Okay, combustion heat. Product minus reactant. N here refers to the number of moles of each component. Okay, and the H is in kJ kmol. Now this one, the N here refers to number of moles. So you must generate the combustion equation first. What is your reactant? How many moles of air required? Then how many moles of product produced? Okay, there are three components in heat in combustion. Heat of reaction, the combustion itself, the sensible heat of the products, okay, at certain temperatures. When you are given temperature, based given temperature, let's say T equivalent to 1000 Kelvin. So sensible heat is enthalpy at a given T minus enthalpy at reference. That means enthalpy at 298. Okay, that is sensible heat. Latent heat will involve when there is phase change. Okay, sensible heat, temperature change without phase change. Remain at the same phase. Okay. Sensible heat without without phase change. Latent heat involve phase change. Okay, common reference state 35 degrees C, at 1 atm. Okay, you'll see later on the enthalpy at reference state would be a superscript denoted as O1. Okay, here. This is the reference state at 35 degrees C and 1 atm. Okay, so enthalpy of a chemical component is the sum of enthalpy of the component at 35 degrees C and the sensible heat of enthalpy. Okay, enthalpy of a component, enthalpy at 35 degrees C plus the sensible heat. Okay, this is the heat of formation at reference state 35 degrees C, 1 atm. Enthalpy at 298, 25 degrees C as well. This one. Okay, this one. Enthalpy at reference. Enthalpy, this one. Okay, this enthalpy is at given temperature. This one. Okay, this one, enthalpy at a given temperature. Okay. This is heat of formation, HF. Okay, for heat of formation, you have been familiar this term in thermodynamics, right? Heat of formation is the heat generated when the component is formed. Okay, so for here in this reaction, to form H2O, you react O2 plus H2. So you get H2O. Okay, so this is the heat of formation of H2O. Now H2O, they have it has two phase, liquid and vapor. So this is for liquid, heat of formation of liquid. Always check on the phase because they have different value for liquid and gas. Now this one is the heat of formation of CO2, where the reaction occurs carbon plus O2. Then you get CO2. So this is the heat of formation of CO2. Okay, this standard heat of formation you can find in table A26 in thermodynamic properties table. Okay, this one is for liquid. This one is for CO2. And let me share with you the table. A26. Water, we have water vapor and water liquid. Okay, so this is the heat of formation for both water vapor and water liquid, HF. Check on the HF column. Okay. Now back to the slide. And this one, repeating the same thing, enthalpy is equivalent to heat of formation plus the sensible heat. Okay. Now we straight away go to the example. You can see, because later on I need to open the table side by side. Yeah. Now a gas stream at 1 atm mixture contains a mixture of CO, CO2, and 2, in which the CO mole fraction is 0.1 and CO2 mole fraction is 0.2. Okay, you have a combustion system where here it doesn't mention what type of fuel used plus the air. Okay. Now the product you have here is CO, CO2, and 2. CO mole fraction is 0.1. Okay, CO mole fraction 0.1. CO2 mole fraction is 0.2. Now, how to get the mole fraction of N2? Mole fraction of N2, this is 0.1, 0.2, N2, 1 minus 0.1 minus 0.2. Okay, 1 minus 0.1 minus 0.2, equivalence to 0.7. Okay, why 1? Because this is in fraction. Total should be 1. Temperature given is 1200 Kelvin. Okay, at 1 atm. T given 1200. Okay, it asks you to determine the absolute enthalpy of the mixture, H mix, on both a mole basis and mass basis. Okay, we know that enthalpy of the mixture, that means enthalpy of the reaction, combustion reaction. So it is product and H product minus total of NH reactant. Okay, but now it gives you only product. It asks for enthalpy of the mixture. So mixture only. So we find out what is the mixture of the product. Enthalpy of the mixture in the product. Okay, so this one. Now this H mix is the enthalpy of the mixture, equivalent to total enthalpy of the products. Products we have CO, CO2, and N2. Okay, so mole fraction of the CO multiplied by heat of formation of CO plus sensible heat of the CO. So that means 0.1 CO, mole fraction of CO, multiplied by heat of formation of the CO. Heat of formation CO plus enthalpy at the given T. That means at 1200 minus enthalpy at reference. Okay. Now we should find what is the CO, heat of formation, for each gases, enthalpy of each gases. Okay, I would suggest you to do in table form. Okay, I'll show you the step by step. So we have CO, CO2, and N2. The required info that we need: H, heat of formation of each, heat at that particular temperature, and enthalpy at reference. That means at T298 Kelvin. Okay, now we check the table. Okay, I open side by side. Which table to refer? CO, HF, heat of formation, table A26. Heat of formation is always at table A26. So we find CO. CO, heat of formation, 110530. Negative, 110530. Heat of formation. CO. So CO2, negative 393. 520. Heat of formation nitrogen. What is it? 0. Nitrogen 0. Okay, on heat of formation. Okay, first step, find the heat of formation. Any question? Yeah, table A26, heat of formation. Now we move to the enthalpy at that particular temperature, which is 1200 for CO. Okay, for CO, you find using table CO. This is OH. O, H2O, CO. Okay, table A21. 1200. Okay, what is the value of the enthalpy? 1200. This is the value for the enthalpy. I'll make it bigger. Okay, table A21 at 1200 Kelvin. So the value is 37095. Okay, at that particular temperature. Now we should find the enthalpy at reference, T298. Okay, come Jarian, finish. Okay. Now find at 298. Make sure CO. Okay, CO. So 298. This is the enthalpy at 298. 298. Find the enthalpy. 8669. Okay. Do the same for CO2 and N2. Okay, now for CO2, to find the enthalpy at the given temperature, find ideal gas properties for CO2. Okay, this table A20. They are at different table. CO just now A21. Now CO2 is table A20. 1200. Okay. Okay, now find for enthalpy at reference T298 Kelvin for CO2. 298, so we move upward. CO2, 9364. Okay. Next for N2, find which table is related to N2. Here, table A18, N2. 1200, the enthalpy at 1200. 36777. Okay, next find enthalpy at 298 for N2. Still table A18. Eight, 6, 6, 9. Okay, let me know if I go too fast. Okay, we see here the enthalpy at 298 for N2 is similar to CO. Okay, let's double confirm. Enthalpy at 298 for CO. Let's check back. Yeah, same. CO table A21 at 298, it is 8996. Sorry, 8669. Okay, same. Now we have got the infos for each gases. Okay, any question on extracting the info from the table? Can? So it involved from A18 until A27. Okay, so now from here, once you get the info for each of the gases, plug in into this equation. CO, CO2, and N2. Okay, we know the mole fraction of N2 is 0.7. Then multiply by heat of formation of N2, which is 0, plus the sensible heat of N2. So this at particular temperature and at reference. Okay, please ignore this figure. This figure is not from the same table that we use. This figure is not the same, so please ignore this figure. Your final H mix will be different from this. You should be getting around negative 5834.2 kilojoule per mole, kilojoule per kilomole. Okay, just use the info that we get from the table, plug it into this equation. Try to calculate. It is not also only for the future, but there's no included. Still part of that for the still and the products only.
That emotion that you brought is also acceptable.
The one for the overall combustion. Overall combustion. Okay, so you should be getting 58,342 for the H mix kilojoule per K mole. Now to find the H mix in mass basis kilojoule per kg, so you should find the molecular weight of the mix first, where the mole fraction multiplied by each of the molecular weight of the component. Okay, sum up all together, then you will get the molecular weight of the mix. Once you get the molecular weight of the mix, then recalculate for the enthalpy of the mixture in mass basis, because you will need in kilojoule per kg. Okay, so you should be getting your H mix mass basis 1811, around that figure. Okay, clear? Anyone need my assistance to explain further? What do you get for H mix? 1811 or 1869? Yeah. What, yes? Which one? 1869, huh? 1869.22, right?
Rectangle product.
All of you get 1869. There's some error over here. Okay. Yeah, so I proceed to the next slide, where the first law analysis of reacting system, we know that E in equals to E out. Energy in equals to energy out. So energy in, considering you have the heat, the work, and reactant. Okay, total heat produced by the reactant, equivalent to the E out. Q plus W plus the products. The energy transferred out by per mole of fuel. So in summary, Q minus W equivalent to H product minus H reactant. Okay, Q here means Q in minus Q out. Okay, W here, W in minus W out. Okay, equivalent to H product minus H reactant. H product, whatever product that you are producing, summation of mole multiplied by the heat of formation plus sensible heat. Okay, for the product and for the reactant. Okay. Now this one, this equation, don't confuse yourself. This one is reactant minus product because it only focuses on the Q out. Okay, Q out, that's why you see reactant minus product. From the original equation over here, so Q out equal to reactant minus product. Okay, Q out. This one, the product, bring to this side. You will see reactant minus product. Okay. Don't confuse yourself. This one is Q out only. Okay, this one, Q in minus Q out, the total Q, equivalent to product minus reactant. Okay, product minus reactant. Later, in all of our calculation, we will use this equation, product minus reactant. Okay. Don't get confused by this equation. Now, for example, we have methane as fuel. Methane as fuel. Assume complete combustion. So your product will be CO2, H2O, and N2. First thing first, as we did earlier, you must generate the combustion equation first in order for you to proceed with the enthalpy calculation, heat calculation. Okay, this part must get correct first, where you need to calculate the A mole produced for CO2, mole produced H2O, and 2. Okay, this one must get correct first. If this one wrong, then the whole of the calculation will be wrong. Okay. Okay, now we know for the Q, heat of combustion, product minus reactant. Reference we take at 25 degrees C and 1 atm. Okay, and that the product produced is in liquid form. H2O is in liquid. Okay, so we know heat of combustion equals to summation of product heat minus product heat of the reactant. Product minus reactant. Okay. Using this combustion equation, we know each of the mole in reactant and in product. Okay, so find out what are the infos for the components, where here you have CO2, H2O in liquid. Sorry, this one is vapor. Sorry, H2O in liquid and the methane. What else that you need over here? The component. Here it listed CO2, H2O, CH4. What else do you need? Now, these components. Product is CO2, H2O, and N2. But here there is no N2. So you must find out for N2 and the O2 as well as your reactant. If product is this part is your product, CO2, H2O, and N2. Reactant, it involves your methane, O2, and N2. Okay. Now list out all components, identify what is your product's component and also reactants component. Then find out the HF, the H at particular temperature, and also H at reference. Okay, here. What is the given temperature over here? There is no given temperature in the input, right? So we assume at 25 degrees C. Since there is no, sorry, here, reactants and the product, it already mentioned, sorry, reactant and the products are at 25 degrees C and 1 atm. So, HC is equivalent to sensible heat. Sorry, H at T equivalent at H at reference. So is there any sensible heat involved? No, right? Because heat at particular temperature is the same as enthalpy at reference. Because here is also 25 degrees C. This one is also 25 degrees C. How do we know? Here, they already mentioned. Both reactants and products are at 25 degrees C. So there is no sensible heat involved. Okay, because no changes in temperature. So here, product is CO2, H2O, and N2. One CO2 multiplied by heat of formation of CO2. Heat of formation of CO2. Okay, supposedly plus sensible heat, but we don't have sensible heat over here. So we just ignore. Okay, then plus 2 of H2O, 2 mole of H2O, then heat of formation of H2O liquid. Plus nitrogen 7.52 heat of formation nitrogen, where we know heat of formation of nitrogen is 0. So that's why in the table it doesn't state. Okay, but I will advise you to state everything. Okay, now this part is only for product. Minus reactant. Your reactant is methane. 1 mole of methane multiplied by HF of methane. Okay, plus O2, 2O2. We know that there is no heat of formation of O2 and also heat of formation of N2. Okay, I will just write first so that you don't get confused. Okay, so product, this part, minus reactant. Heat of formation N2 is 0, so we can cancel out this one. Heat of formation of O2 is 0, cancel out, then cancel out of N2 as well. Okay, so that's why in this solution, you will see multiply CO2, this part is CO2. This part is 2 multiplied by negative 285 is the HF for liquid, water liquid. Okay, minus 1 multiplied by 74 over here is the HF of methane. Okay, this one is the methane. So you will get this figure of the heat of combustion in kilojoule per kmol. Okay, where you can find the heat of formation? Which table? Heat of formation. A26. Okay. Heat of formation. Table A26. Okay, if the question asks for the mass basis, so the heat of combustion in kilojoules per kmol divided by the molecular weight of the fuel. Then you will get kilojoule per kg. In this statement, it mentioned water is liquid. So you must get the heat of formation for H2O liquid. Okay. But if the question doesn't mention whether it is vapor or liquid, you can assume. You can pick either one, vapor or liquid. Okay. Okay, can I move? Okay, this slide, if the water product is in vapor form, okay, then the value will be different for the HF. Final answer will be slightly different as well. Okay. Okay, here it mentioned the two values of HF of water. You have liquid and vapor. Okay, the difference between the two enthalpy is equal to HFG. Liquid minus vapor. Okay, you will get HFG. Another term, it is defined as heating value. Okay, for this one, heating value is called the higher heating value, HHV. Okay, remember in chapter 1 for the calorific value calculation, NCV, GCV. Okay, it is also different when you have water in liquid and water in vapor, right? GCV is HHV when the water is in liquid form. NCV equivalent to LHV when water in vapor form. Okay. LHV when H2O in vapor form. Now the equation that relates HHV and LHV is this equation where HHV is in liquid form, water in liquid form, LHV in vapor form. So HHV is equivalent to LHV plus M, the mass of the water. In this case is water, we are referring to water, multiplied by the HFG, the difference between enthalpy for liquid minus vapor. This now. HFG is the enthalpy of vaporization. The heating value or the enthalpy of combustion can be determined from the enthalpy of formation. Okay. I'll share with you side by side with this one. Okay, for methane, for example, methane in table A27. Methane. A27. So methane, we have HHV and LHV. In table A27, it already mentioned to you the value of HHV and LHV. Notice that this is in unit kilojoule per kg. Okay, so if you need to find kilojoule per kmol, multiply with the molar mass. This one is HHV for methane, LHV for methane. Okay. Table A27. HHV from here for methane. HHV is this one. Okay. To get this figure, multiply by the molar mass. Then you will get this figure, 890 in kilojoule per kmol. Same goes with LHV. The figure given in the table, okay, this one, multiply by the molar mass. Okay. Okay, now we go to this example where we have fuel liquid octane. Okay, the fuel here is liquid octane at 25 degrees C and 1 atm. So the inlet to the combustion chamber is 25 degrees C and 1 atm. Using enthalpy of formation from table A26, assume the water in the products is in the liquid form. The water here produced is liquid form. It asks you to determine the enthalpy of combustion. Liquid octane react with the air. Air, we know here it is O2 plus 3.76 N2. Okay. First step, find the combustion equation. Okay, generate this one first. Find out what is the A over here. From there, find out what is the mole of CO2 produced, mole of H2O liquid produced, and total mole of N2 produced. Okay. Now, how to get this A? Ibrahim, how to get this A? Four, okay, over 4. X is 8 plus Y 18 over 4. Okay, what you get?
Like
4.5. Huh? 12.5. 12.5. Okay, then generate the final combustion equation. 12.5. So this one 3.76 multiplied by 12.5. Okay, to find the enthalpy of combustion, enthalpy of the product minus enthalpy of the reactant. Okay, again, list down all the infos that you required. Component, your octane. Okay, reactant is your octane, O2 and N2. Product would be CO2, H2O and N2. Okay, then find out what is the HF of each component. This one from table A26. Do you need the heat? Is there any sensible heat involved? No, because same temperature. Inlet 25, outlet 25. So there is no sensible heat involved. So you will need only the heat of formation info. Okay, find out from the table A26. For propane, octane. Octane. Your octane given here is liquid. Okay, make sure you extract the correct info for liquid. Okay, and octane liquid. So the HF is 249. Right, 249. HF for liquid octane. Negative 249. 950. O2. What is HF for O2? 0. N2? 0 as well. CO2? 393. Negative 393. 520. H2O liquid. Okay, 285,830. Negative 285,830. Okay, then plug in into the equation. Product, which is your CO2, 8 mole multiplied by heat of formation. Okay, this part is for CO2. This part is water, liquid. This part is your fuel, octane, the reactant. Okay, so you should be getting around this figure. if your product is in vapor form, so this amount of HF will be different. Okay. Figure of HS will be different for water vapor. Okay, any question? Anyone need me to repeat? Clear? Now we try to do this example where you have liquid propane as your fuel. Liquid propane enters a combustion chamber at 25 degrees C at a rate of 0.05 kilojoule per minute, rate of the fuel. Okay, and it is mixed and burned with 50% excess air that enter the combustion chamber at 25 degrees C. An analysis of the combustion gases reveals that all the hydrogen in the fuel burns to H2O, but only 90% of the carbon burns to CO2, remaining 10% forming CO. Okay, if the exit temperature of the combustion is 1500 K, so determine the mass flow rate of the air and the rate of heat transfer from the combustion chamber. Okay, here you are given a fuel liquid propane at a rate 0.05, temperature in 25 degrees C, both fuel and reactant. Temperature out 1500. You have CO in your gases. Okay, and excess air. Now, first thing first, always find the combustion reaction. This is the theoretical amount air for theoretical combustion reaction. Okay, from stoic, the A calculated from the stoic, from the given fuel, which is the propane. Okay, you get A stoic equivalent to 5. Okay, then the balanced equation for the actual combustion process is 50% excess air. 50% excess air. So it means over here, theoretical air, how many? 50% excess air. So theoretical air equivalent to 1.5. A stoic, which is the 5, multiplied by 1.5. That's why here you get 7.5. Okay. Again, I repeat, 50% excess air. So theoretical air is 1.5. If no excess air, theoretical air would be would be only 1. Theoretical air 1 is meaning that no excess air and export. Okay, now we have excess air. So theoretical air is 1.5. 1.5 multiplied by the 5, the A is 5. You get 7.5. So from here, 7.5, the N2, 3.76 multiplied by 7.5. Okay, this one, 3.76 multiplied by 7.5. That's how you get 28.2. Okay. Now, the question mentioned that only 90% of the C burns to CO2. See here we have 3. Okay, 90% from the 3. What is it? 90% from the 3. 2.7 forming CO2. Okay, 10% forming CO. So 0.1 multiplied by 3 equivalents to 0.3 CO. Okay, so that's how it gets 2.7 over here, 0.3 CO over here. Okay. Can this part, anyone need me to repeat? Ibrahim, are you clear? Okay. Now we already have all infos. Generate the finalized combustion equation. Okay. So to find the mass flow rate of the air, we know that M air is equivalent to, AF is equivalent to M air over M fuel. Sorry? Water multiplied by the O2, 2.65 over here. You need to do the O balance. So here, do the O balance, left side and right hand side. Okay. So here, 2 multiply 7.5 equivalents to 2.7 plus 0.3 plus 4 from the water plus, here just now is unknown. So let's say I put B, 2B. Okay, so from there, do the balance, you'll get the B equals to 2.65. Okay. You must do the O balance in order to get the unknown. Initially, this is unknown. 2.7 and 0.3 we can get from this statement. Nitrogen 3.76 multiplied by the A. Water, this one we can get from the Y over 2. Okay. Okay, now moving forward to find the mass flow rate of air. We know that the AF is equivalent to M air over M fuel. M fuel, the flow rate of the fuel is given. Okay, we should find M dot air. But we need to calculate the AF first. Okay, so AF equation, M air over M fuel. This is your A actual multiplied by 4.76 multiplied by molecular weight of the air divide by M fuel. Okay, you get the AF. Once you get the AF, plug in into the equation over here, then you will get M dot air. M dot fuel 0.05. It is given already. Okay, so this is your M dot air. Okay, I will need to stop here first. We will proceed next class on B calculation. For B, we will do step by step. Okay, it will be quite long. So we will proceed on Friday. Okay, so if any question before we stop, we have 2 minutes left. Okay, make sure you recall back from the recorded lecture. If you have any question, you can ask me through the Teams or in next class. Okay? Okay, so that's all for today. Thank you, class.